Welcome friends to this new lecture of soil science and technology, and in this lecture we will be finishing the silicate clays because we have started the silicate clays, and we will be talking about X-ray diffraction analysis, and after we cover the X-ray diffraction analysis I will be going to the next topic, that is different sources of charge development in the clay minerals. And so, let us talk about X-ray diffraction analysis. Now, as I have already told you that d-axis spacing is very much important for the identification of the clay minerals, because one clay mineral differ from another clay mineral based on their d-axis spacing. As you can remember, the d-axis spacing of kaolinite is the smallest, that is 0.72 nanometer, followed by illite, which is also nano expanding. Then we see 1.4, which is for nanometer for 0.14 nanometer for kaolin for chlorite. If we go back and see, there is 1.4 nanometer, then 1 nanometer for illite, 1 to 1.5 nanometer for vermiculite, and 1 to 2 nanometer for smectite or montmorillonite. So, you can see there are differences in their d-axis spacing, and basically we use these structural difference for their identification using the X-ray diffraction analysis. So, what is X-ray diffraction? So, if you can see, these are some parallel atomic planes. Obviously, you know what are the parallel atomic planes and what is the d-axis spacing. I have already discussed this. So, the distance between these parallel, distance within these parallel two lines of atoms is d-axis spacing, and suppose there are two different incident X-rays which are diffracting from the different planes. So, let us consider this is the ray 1 and this is ray 2. So, you can see the ray 1 is coming and ultimately it is getting diffracted from the first layer. So, this is the diffracted ray, and also in the second, the ray also getting diffracted from the next parallel atomic planes from this plane. So, the distance of atomic planes d, that is the distance of these atomic planes, or d, can be determined based on Bragg's equation, which is given by scientist Bragg. Now, Bragg says that BC plus CD is, or in other words, Bragg's law says that the two rays will constructively interfere if the extra distance ray 2 travels is a whole number of wavelength farther than what ray 1 travels. So, what is constructive interference first of all, and what is destructive interference? So, let us consider this picture. Obviously, you can see these two waves are in phase, and when those two in phase waves combine, they will form this constructive interference, which will have higher amplitude than individual these individual waves. And here you can see these two waves are out of phase, so they are basically nullifying themselves. So, this is an example of constructive interference and this is an example of destructive interference. So, the two rays, here you can see this is ray 1 and this is ray 2. So, these two rays only can constructively interfere if the extra distance travelled by this ray 2 will be an integer multiplier of the wavelength of these incident rays, and the wavelength is lambda. So, you can see what is the distance this ray 1 travelling. The ray 1 is travelling A and from A to here, and the ray 2 is travelling, the extra distance ray 2 is travelling this BC plus CD. this is the extra distance that ray 2 is traveling. So, BC plus CD has to be an integer multiplier of the wavelength of incident ray. So, if the incident ray wavelength is lambda, obviously then n is the integer, and these, in other words, n lambda is basically 2d sin theta, because BC equal to d sin theta. Theta is the angle that it makes, this is the angle theta, and BC and also CD is another d sin theta. So, BC plus CD equal to 2d sin theta, or in other words, n lambda will be 2d sin theta, which are, or in other words, d will be n lambda by 2 sin theta. So, this is the basic form of this Bragg's law, and different clay minerals. Now, these d will vary from one clay mineral to another clay mineral, and different clay minerals have various basal spacing or atomic planes, or in other words, d axis spacing. For example, the basal spacing of kaolinite is 7.2 angstrom or 0.72 nanometer. So, based on these principle, you can separate one clay mineral to another clay mineral. So, based on these d axis spacing, you can separate one clay mineral to another clay mineral. So, basically the technique we use for separating the clay minerals or identifying the clay minerals is called XRD technique or X-ray diffraction technique, and basically you will, in the X-ray diffraction technique, you will see some peaks like that, and as you can see, we are having the kaolinite peaks arising at 7.2 angstrom, around 7.2 angstrom, and by changing the 2 theta value, we can get the second order peak also at 3.56 angstrom, which is basically 7.13 divided by 2. So, you can see these d axis spacing can be exactly identified by using the X-ray diffraction analysis, and these using this X-ray diffractogram, by the way we call it X-ray diffractograms. Using this X-ray diffractograms, you can identify the individual clay mineral. So, this is about the X-ray diffraction analysis, and there are also there are several details about X-ray diffraction analysis, and we are not going in details. However, if you are interested, you can consult any book which deals with the X-ray diffraction analysis to gain better understanding of the process. So, guys, we have completed the silicate clays. I hope that you have learned something new in the silicate clays. This is very important, and then in the next topic will be sources of charges in the soil colloids. So, let us start. And in this lecture, we will be covering, in this topic, we will be basically covering these following concepts. We will be covering the constant charges in colloids, then we will be covering variable charges in colloids, and then we will be talking about adsorption of cations and anions to colloidal surface. So, let us talk about types of charges. Two types of charges arise in soil colloids. One is called constant or permanent charge, and these this another charge is called dependent or variable charges. Now, constant and permanent charges occurs because of isomorphous substitution. I have already talked about isomorphous substitution in our previous lecture, and we will be talking about this pH dependent charge or variable dependent charge. Now, remember that this variable charge depends on the solution pH, that is why it is also called pH dependent charge. So, these are two major sources of charge that develops within the soil colloid. So, we will discuss them one by one. Let us start with the constant charge. Now, constant charge arises due to the isomorphous substitution, and it is called constant or permanent because it does not depends on the variable pH. It is constant, it depends on the internal structure of the clay mineral. So, it is not dependent on pH, it only depends on isomorphous substitution, which is basically replacement of cation by another cation of similar size and depends only the type and abundance of the cations. And obviously, this type of isomorphous substitution basically you can see in 2:1 type of clays like montmorillonite, like vermiculite, and like illite. I have already discussed them in our last lecture. So, this negative charge arise basically when a lower charge of cation replace higher charge cation. We have discussed about that replacement of alumina with Al3 plus with Mg2 plus in octahedral sheet, and also replacement of Si4 plus with L3 plus in a tetrahedral sheet in case of fine grained mica, if you remember. So, these are some examples of isomorphous substitution, and as a result of this isomorphous substitution there is the development of constant or negative permanent charge. I have discussed already this picture in our last this diagram in our last lecture. So, I am not going to in details, but just to give you just to a brief idea, you can see aluminum 3 here is replaced by magnesium, and obviously occurs in, and this type of thing occurs in aluminum dominated dioctahedral sheets of smectite, vermiculite and chloride. So, we talked about constant charge, they are basically negative, but sometime positive constant charge also develops. So, how they develop? Remember that positive charge arises when a high charge cation replaces lower charge ion. It is, for example, when L3 plus replaces Mg2 plus in trioctahedral sheets, and it is common in trioctahedral hydroxide sheets or in chlorides. So, this is an example where positive constant or permanent charge also can develop within the clay. Now, what is variable charge or pH dependent charge? Now, pH dependent charge or variable charge is mainly found within 1:1 type of clay like kaolinite and humus. Remember that humus is the organic colloid, and it is one of the major component of soil. And remember that this 1:1 type of clay and kaolinite and humus basically shows variable charge because exchange occurs in the external surfaces only. And remember that they may give rise to both positive and negative charge. That is why we are calling it variable charge, because they can generate either positive charge or negative charge. However, in case of constant charge, it is mostly negative charge. So, in case of variable charge or pH dependent charge, it depends on pH of the soil solution. Now, so what is variable charge? Variable charge, I mean, you can see here, this is a neutral pH. Now, you know that clay mineral contains different layers of atoms like hydroxyl, followed by aluminum, then followed by oxygen hydroxyl, then followed by silica, then followed by oxygen. In case of 1:1 type of layer, obviously 1:1 type of layer. So, these are some edges. So, when these type of edges are present, obviously you will see that there will be hydroxyl group which are present at the edges, broken edges of aluminum. And in case of lower pH, that means when there will be lower pH, when there will be high dominance of protons, we know that. So, this proton will go and attach to this hydroxyl to form this positive charge. And so, you can see at acidic condition, in acidic condition, these 1:1 type of clay or edges of the 1:1 type of clay, they can produce the positive charge. However, in case of high pH condition, that means in alkaline condition, there will be dominance of OH minus, and this H will react with OH minus to produce H2O, and ultimately leaving this O minus. So, they are ultimately creating negative charge. So, you can see based on different pH, the charge distribution is also changing. In case of lower pH, you are getting positive, there will be development of positive charge, and in case of higher pH, there will be development of negative charge. So, that is why we call it variable charge. All right. So, development of a pH dependent charge in kaolinite is a specific example. Obviously, let me show you. So, this is a 1:1 type of layer, and in this 1:1 type of layer, one charge from octahedral oxygen that has lost is hydroxyl. So, you can see one hydroxyl is getting lost from here, and we are getting a net surface charge of -3, and the crystal edges one hydroxyl will attach to this one proton will attach to this -half to create positive half. So, here we are getting net negative charge -1, and ultimately we are also getting net surface charge of +1. So, you can see as pH decreases from left to right. So, here pH is decreasing from left to right. So, that means in lower pH condition there will be higher dominance of H plus. Higher dominance of H plus will produce more positive charges at the edges. So, you can see with the increase of the pH, the net surface charge is getting positive from -3 to +1, and obviously you can see here how these protons are getting attached to these edge, these hydroxyl groups which are present at the edges or broken edges. Okay. So, I hope it is now clear to you. So, let us go and see variable charge. Okay, we have discussed about the negative charge. Obviously, this positive charge occurs under moderate to extreme acidic condition, and obviously under low pH H oxygen associate with H plus, hence a net positive charge. I have already told you that. So, let us see that these are charge characteristics of representative colloids showing comparative levels of permanent and pH dependent negative charge. You can see one thing, that in case of organic, the constant charge is percentage of negative in the total negative charge. Obviously, the percentage of constant charge is only 10%. However, the pH dependent charge is 90%. So, in case of smectite also, the constant charge is 95% because of isomorphous substitution. However, there is only 5% pH dependent charge because they do not show this type of broken there is no such positive charge development at the or negative charge development at the edges. As you can go from organic then to smectite, vermiculite to kaolinite, now you can see 95% of the negative charge is based on pH dependent charge, because the constant charge is only 5%. Why it is that? Because if you remember, they have almost lock structure due to the presence of hydrogen bonding in between the adjacent layers. As a result, no cations and another moreover, there is no isomorphous substitution in case of kaolinite. As a result of less isomorphous substitution in the kaolinite, obviously there will be no constant charge or negative charge development, only they rely upon the pH dependent charge. However, in case of gibbsite and goethite, they are extreme condition. Obviously, there will be 100% pH dependent charge. There will be no constant or permanent negative charge. Okay. So, what is the relationship between pH and charges? So, obviously, cation exchange capacity increases with increasing soil pH. It is quite obvious, because you can see here the relationship between soil pH and surface charge. So, as you can see, the soil pH is increasing, the negative charge increasing, or in other words cation exchange capacity is increasing, or in other words, as the soil pH is increasing, the negative charge increases because of pH dependent charge, and as a result of that, there will be more cation exchange capacity, or in other words there will be more ability for the soil to absorb more positive cations. So, that is why cation exchange capacity increases with increasing soil pH. However, anion exchange capacity decreases with increasing soil pH. As you can see, the soil pH is increasing from 3 to 4 to 5 to 6 and 7, and positive anion exchange capacity is getting decreased here from 0.3 almost 0.2.5 plus 2.5 to around 0 at around 7 soil pH. Because of that, I mean, and why is that? Because as we are increasing the soil pH, negative charge further develops, and as a result of the negative charge develops, that will create the repulsion of the negatively charged anions, and as a result of that, anion exchange capacity will decrease. Now, what is cation exchange capacity? So, before discussing this, what is cation exchange capacity and anion exchange capacity? Cation exchange capacity is the soil to absorb the cations from the nearby environment, whereas anion exchange capacity is basically the ability of soil to absorb anions from the nearby environment. Remember that since cations are positive, negative charge has to be developed over the soil surface for their attraction, and electrostatic attraction forms between these cations and this negatively charged surface of the clay minerals. So, and in case of anions, obviously this is because of pH dependent charge, and pH dependent charge in the low pH condition, or acidic condition, obviously there will be positive charge development, and this positive charge will attract the negative charge anions like nitrate and sulfates, and they will attach to the soil surface. So, this is anion exchange capacity and cation exchange capacity. So, I hope that now it is clear why cation exchange capacity increases with increasing soil pH and anion exchange capacity decreases with increasing soil pH. Now, in acid rich 1:1 type of clay soils, in the tropical regions, positive charges are more abundant, whereas negative charges predominant in 2:1 type of clays in temperate region. It is quite obvious, because 1:1 type of clay is kaolinite, and kaolinite can only generate this pH dependent charge, not the permanent charge due to isomorphous substitution. So, obviously clays are negatively charged, because this is a very good experiment, and where they have scientists have placed 2 electrodes, and obviously you can see the clay attracted to the positive terminal and demonstrated it is negative charge. So, clay particles are negatively charged, and these negative charge develops predominantly from the isomorphous substitution or constant charge. Now, adsorption of cations and ions. Adsorption, remember that it is basically, some examples are adhesion of gases, ions or atoms to the surface, and it may be either physical or may be chemical, and charge colored surface absorb cations and anions. Two types of formation aid in adsorption. One is outer sphere and inner sphere complex. So, let us discuss what is outer sphere complex. Outer sphere complex is when ions are usually surrounded by water in soil solution, and water molecules thus acts as a bridge between the ions and colored surfaces, and this weak electrostatic force bind the ions and to the colloids, and ions are easily replaceable. So, this is outer sphere complex. What is inner sphere complex? Inner sphere complex is when no water molecule between the ions and colloids, hence ions directly bound, they are bond with colloidal surface, and they are very difficult to replace ions. So, here you can see tightly bonded K plus ions. So, these are example of inner sphere complex. This is an example of fine grained mica or illite. If you remember, in case of illite, there is only isomorphous substitution in the tetrahedral sheet. So, as a result of that, the inner layer is occupied by the small potassium cations, and these potassium cations forming this inner sphere complex, they are not surrounded by water hulls. So, these are example of inner sphere complex. So, this picture shows in a nutshell what is inner sphere and outer sphere complex. So, you can see there are two types of surfaces. Obviously, these are negatively charged sites where you can see negative charge developed due to isomorphous substitution, and these are positively charged site which occurs due to variable pH, and these negatively charged sites are basically attracting different cations, and obviously this is an outer sphere complex, calcium ion surrounded by water molecules, they are getting attached here, and also this is an example of inner sphere complex where this H2PO4 is getting attached directly to the to the clay. So, it is hydroxylated surface of kaolinite and gibbsite. This is an hydroxylated surface of kaolinite and gibbsite example, and basically both outer sphere complex and inner sphere complex are diffused in the nearby soil solution. So, this is why this is called outer and inner sphere complexes, and now I hope it is clear to you what is the difference between outer sphere complex and inner sphere complex. So, roles in adsorption, obviously the amount and type of cation adsorbed affect the fertility of the soil. Here you can see a list of different cations and anions which are having different different roles for the growth of the plants. Obviously, ammonium is a plant nutrient, there is a plant nutrient, aluminum is toxic to the plants, calcium is a plant nutrient, cadmium is toxic pollutant, so on and so forth. So, these roles of adsorption, they are having high roles in adsorption because based on their dominance they can influence both the soil fertility as well as plant growth. So, we have finished the different sources of different charges in the clay colloid, in the soil colloid, and I hope that this lecture was informative to you and you have learned something new. And if you have any queries, feel free to send me an emails and send the emails to my TAs. So, they will be more than happy to help you, and let us wrap up here, and in the next lecture we will be starting a new topic. Thank you very much.